Alright, it is very important as a chemist to be able to run some type of analysis on something and get data and interpret that data into hopefully determining the structure or the formula of a completely new compound. So in calculating empirical formulas, or finding empirical formulas, that essentially is what we're going to do. We're going to be given a certain set of data, some type of analytical data, typically some type of instrumental analysis, and we're going to have to, from that data, determine an empirical formula. Okay, well, how do we do that? Well, if our data is given to us in the percent, for example, if we run it through a machine and the machine tells us so much percent of the compound is carbon, so much percent is hydrogen, so much percent is oxygen, so much percent is nitrogen, we can perform, or we can find the empirical formula, or the simplest form of the formula, by going through several steps. Okay, if given the percentage, we're going to assume a 100-gram sample. All right, once we get to grams, we can then go to moles. Okay, remember our ultimate goal in chemistry. If we can get everything back to the mole, we can do a lot of different stuff with it. So we can use the molar mass to go from grams to moles of the element to calculate a mole ratio for our empirical formula. Okay, well, that seems simple enough. Well, let's look at an example problem. The compound para-aminobenzoic acid, commonly used in sunscreen. It's a UVB blocker. I don't know if they use it quite that much anymore. It's also used to treat irritable bowel syndrome. For those of you who may have issues with that, I suppose I should say. It's composed of carbon at 61.31%, hydrogen at 5.14%, nitrogen at 10.21%, and oxygen at 23.33%. Find the empirical formula of PABA, okay, or para-aminobenzoic acid. All right, empirical formula, you should remember, is the simplest formula. The empirical formula is the simplest ratio. Molecular formula tells us the actual structure of the compound. So let's look at it. It gave us the percentages. Okay, since these were percentages, we can assume that we have 100 grams. Those percentages then can correlate directly into a gram measurement. Hopefully this adds up to be approximately 100, maybe 99 or so, maybe even a little over 100, but we can work with that. Once we have it in grams, we know that we can go from grams to moles of a substance by simply using the molar mass. Okay, we get the molar mass from the periodic table. You should remember that's grams per mole. Remember, we use 2 decimal places. Then we come up with a molar amount for each of these different elements present. Well, how are we going to make this a formula? Well, we simply take the smallest number of moles and divide each atom or each element present by the smallest number of moles. That will in turn give us a ratio of these different elements. Okay, essentially what it says, for every 0.7288 moles of nitrogen we have, we're going to have these many different moles of the other elements. Well, how can we normalize that? Well, we divide by the number of nitrogen, and that will give us an approximate whole number for each of these different elements. So we would end up saying our formula is C7H7NO2. Okay, not very difficult. We've practiced this in class several times, so hopefully you'll be able to perform an empirical formula calculation. We can do the same thing with the same kind of process with a combustion analysis. We take a sample, put it into a combustion chamber, essentially is what it is. We add oxygen because, if we're combusting something, we must have oxygen. It's heated up. It goes from the solid or liquid form to the gaseous form. That gas then flows into copper oxide. Okay? Copper 2 oxide specifically. This copper 2 oxide, since we're working with a hydrocarbon, this is a hydrocarbon, since we're working with a hydrocarbon, will help clean, if you will, any impure carbon monoxide from an insufficient combustion and drive that reaction to a CO2, from CO to CO2. Then the gas will go into the next chamber. That will determine that H2O, or the water absorber, determines how much water is being produced from the original sample. Then it flows into a CO2 absorber, and that determines how much carbon dioxide is absorbed. Okay, well, how can we use this water data and this carbon dioxide data? Well, the carbon is determined by the mass of the CO2 produced. Okay, we know how much CO2 is going to be produced. We can go from typically a gram measurement to the moles of CO2 produced, moles of CO2 to the moles of carbon produced, and that will give us the grams of carbon. We can go from moles of carbon produced to grams of carbon by using the molar mass. We can then determine the hydrogen by looking at the water. Same fashion as we would the carbon. We know how much water will be produced. We could take the amount of water in grams, convert that to moles of water using the molar mass, convert moles of water to moles of uh, hydrogen using the mole ratio within the formula. Then we can go from moles of hydrogen to grams of hydrogen using the molar mass. That will give us the grams of hydrogen produced. And then, using the law of conservation of mass, we know that if it's on one side, it must have showed up on the other side in the exact same proportion. We can take the difference, the total difference from the sample of the carbon and the hydrogen, subtract those two numbers from the total mass, and that'll give us the mass of oxygen produced. Okay. Once we have all that, we can make our mole ratios very similar to the percent composition. The percent empirical formula calculation that we just performed in the previous slide, and that would give us the analysis of that. It may make more sense to you if you actually look at the problem worked out. The ultimate goal of this is we're given a grams measurement typically. We need to go to moles so that we can make a comparison, and we also must take into consideration the law of conservation of mass. We can also do this with element analysis. Right here I have a picture of a copper cycle. We take copper wire, add it to silver nitrate. We end up forming silver ions. The copper will then go into solution with the copper nitrate. Remember the activity series. Copper will replace silver. We end up with solid silver and copper nitrate in the aqueous form. That's why we have this blue solution here. You should remember that copper nitrates are typically blue. And that's about all I want to say about elemental analyses. Now, you may be asked in certain situations to go to a molecular formula. Well, that's real simple. You compare the molecular formula's molar mass to the empirical formula's molar mass. Okay, you will calculate the empirical formula's molar mass. You will be given the molar mass of the molecular formula. Whatever ratio those combine, whatever you divide those, and whatever ratio that comes from that, you will multiply your empirical formula to get your molecular formula.